Hi, I'm Matt Moore, and this is my Math 151 honors project about integrals in Bayesian inference. So what is Bayesian inference? Bayesian inference relies on Bayes' theorem, which I included right here. And Bayes' theorem is based on this fundamental idea that is related to this thought experiment. So if I told you that someone was good at math, would you think that they're more likely to be an actuary or a marine? Now, you might say that they're more likely to be an actuary because we all know to be an actuary, you probably have to be good at math. But the thing is, there's so many more marines than actuaries. The ratios or the numbers are like 25K to 175K. It actually might be more likely that the person is a marine just because there's so many more marines. And the basic idea is this: what we observe doesn't exist in a vacuum. We're really just updating prior information. And Bayes' theorem puts this in mathematical language that I'm going to break down here. And I'm using this actuary marine example. First, you have like the prior probabilities. This is basically just the probabilities or the probability that someone would be an actuary or marine if we're just imagining a world where there's only two possibilities, which I'm later going to refer to as thetas, or what we're really looking for, the outcome that we're expecting. Um, and you can see those probabilities here. The marine having a much higher probability than the actuary. The second component is the likelihood, and the likelihood is how likely is it, or how likely is it that someone in a job is good at math, like one of those two particular jobs. Then there's also something called the marginal likelihood, which I'd prefer to call the evidence to avoid confusion. That's just the overall chance that someone out there in the world, or in our little world where there's only two jobs, actuary marine, is good at math. And of course, I mentioned the prior, which is just or not the prior. I'm sorry, the theta, which would be like what we're looking at, what job is the person going to have, and then the data, and that's the condition. Um, is the person good at math? So when we put that all together, what we're looking for is called the posterior. The posterior is what we're going to compute, and it basically tells you how likely it is that they're in that job, marine or actuary, given that they're good at math. And you're taking the prior and the likelihood, and then dividing that by the evidence, the overall chance, so the overall probability that someone in general is good at math. And what's interesting is in this discrete case, and I'm saying it's discrete because we're using, like round non-continuous numbers, 25K, 175K, discrete probabilities, 20%, 9.95 probability, that like an actuary is going to be good at math. Um, these posterior probability distributions are going to add up to 1, which is what you would expect because we're just looking, at subsets. Each one of these probability distributions is just a subset of something that's going to add up to a total of all the possible probabilities. But what if they don't? Is that even possible? Can you have a continuous probability distribution? Well, in Bayesian inference, there's a lot of applications where this is not only true, but expected. So what happens in that case? Enter the integral. So what you do when you have like a continuous theta, or a probability that could be within, like a range, like between 0 and 1, and you're not exactly sure, or you don't, the prior condition is that unpredictable range, you have to do what's called a normalization. Um, and so instead of dividing by what I like to call the evidence, or dividing the prior times the likelihood by the evidence, you're dividing instead by the integral of the prior times the likelihood, with respect to the theta, the whatever it is that you're looking for. And what that's going to do for you is that's going to substitute for like a discrete evidence. And this works because when you have like a continuous theta, when you have a continuous range of, not possible outcomes, but we'll call them desired outcomes, you're not looking for like a discrete set of possible outcomes, like overall outcomes. You have to kind of like generate that set of overall outcomes with this integral. And you can imagine like a curve created by, this product of the prior times the likelihood, and then the area under that curve being all the possible values between 0 and 1 that you could get in that you can get in the probability distribution that's usually in the numerator. So let's look at an actual example of how this works. So imagine you're stationed at Joint Base Lewis McChord in Washington, where they say it rains a lot, but in reality, sometimes it rains a lot and sometimes it doesn't, and you have no idea when it will or it won't. And you want to estimate how likely it is to rain on a given day. We'll call that your theta. And you don't know what that probability ever is. That's your initial condition. That probability of it raining on any given day is just some value between 0 and 1. Not rain is a value between 0 and 1, and rain is always a value between 0 and 1. It's kind of like your prior. So those values could be like 0.99, or it could be 0.1. So it's entirely possible to end up with a posterior probability distribution greater than 1 or less than 1. So you're going to normalize the data, like I said. And this is, by the way, your likelihood function looks like this. Basically what you're doing is just multiplying the probability of it going to rain twice. Oh yeah, the likelihood, by the way, we're going to say that on 3 days, because we actually have to observe some data to update our prior condition. It's like a continuous. We're not exactly even sure what the prior condition is. So you observe 3 days. 2 days it rains, 1 day it doesn't. So your function looks like this. You're multiplying the 2 days it rains by our theta twice. You take this function, and then you take the integral of that function, and you divide that likelihood times prior divided by the integral that you discovered. It's going to be, in this case, the same as multiplying by 12. And that's how you normalize the data. So when do you use this? Well, it turns out that Bayesian inference is used a lot in machine learning, and it kind of makes sense because the whole concept of machine learning is taking expectations about data, and then in a computational way updating those expectations. And it's very interesting that Bayes' theorem, which when you're using continuous data relies on calculus, is a way of kind of like modeling how we generate knowledge how we understand the world based on our previous understanding of the world and how we update it. So it's just another application. I mean, it's mostly probability, but it's just another application that you might have never considered, that calculus can have a major impact on not just how we understand the world, but how the world works. And as prevalent as machine learning and AI is becoming, that's not going away anytime soon. So thanks, calculus, and thanks for watching my honors project presentation.